All right, math questions. How's the homework going? You said you have a delta question.
61.
What was it? 61 on 1.3?
Yeah.
Oh, yeah, that's a good one. Let's do that one. I understand. So number 61, it's a limit. It's a kind of massive limit.
59 have one.
Yeah. Yeah, 59 probably. It doesn't matter. Oh, 59 is a little easier, but let's do 61. So this is section 1.3.
Yeah.
And it says find the limit as change in x, or delta x, goes to 0 of x plus delta x squared minus 2x plus delta x plus 1 minus x squared minus 2x plus 1 all over. So this is actually a difference quotient in here. Do you guys remember the difference quotient? Yes. Like if I give you a function, the difference quotient, probably if you took 126 here, you saw the difference quotient written as f of x plus h minus f of x over h. So if you evaluated the difference quotient, for example, for the function f of x equal x squared minus 2x plus 1. So if I gave you the function x squared minus 2x plus 1, could you calculate this quotient? Do you know how to do that?
Plug in x plus h.
Yeah, so you would find f of x plus h first. And the way you find f of x plus h is plugging it in for x. So like this. And then you would take f of x and subtract it from f of x plus h. So the difference quotient in this context for this function is equal to x plus h on the squared minus 2x plus h plus 1 minus the actual function. All over h. So now, my point is, if you remember this good, if you don't, fine, we'll go over the difference quotient more in chapter 2. But my point is, you see the similarity here? What's the difference? Well, there's a limit, but besides the fact that yeah, delta x is the same thing as h. Okay? So the idea is, when they write the limit as delta x goes to 0, you think of this as a single variable like an h. Okay? So it's not actually two separate things, it's just one variable going to 0. This whole thing going to 0. This whole thing going to 0. This whole thing going to 0. And it is exactly the same idea as what this h meant in the difference quotient, which is a small change in x. The reason they use delta x here is this represents change in x. You want your change in x to go to 0. Here we use h because delta x was too confusing. So we're going to treat this like just like a single variable, like an h. But even saying that, that doesn't tell you how to do it, right? So now how can we actually, what's the problem if we try to plug in 0 for delta x then? Yeah, if you plug in 0 for delta x, just to try it, you would get 0 on the bottom right away, which is bad. And you would also probably get 0 on the top, right? Because if this goes away and this goes away, all you have left is this function, right? All you have left is this. So this does, believe it or not, evaluate to 0 over 0. Okay, fine. So let me erase my context here. This comes from the difference quotient, but we don't really need that. So I'll erase that and just show you how to find this limit. If you remember, when you were dealing with the difference quotient, you usually multiply things out and try to get things to cancel. Okay. So what I'm going to do here is multiply everything out and hope that a lot of stuff cancels, and then eventually cancel out this delta x. But I have to get this to cancel so I can plug in my 0. So on the top, on the FOIL here, right? This is x plus delta 8, I'm sorry, this is x plus delta x times x plus delta x. I have to do this. That's what x plus delta x squared means. And if you do this, you FOIL. So you'll do x times x, which is x squared, x times delta x, but then x times delta x again, so 2x delta x, and then delta x times delta x. Delta x squared. So that's what I get from this guy. Then I keep going, I would probably distribute out this negative 2 minus 2x minus 2 delta x plus 1, I can't do much with that. Distribute out this negative plus minus x squared plus 2x minus 1 over delta x. You see what happens here? Everything that doesn't have a delta x should drop out. Right? X squared positive, x squared negative. Negative 2x, positive 2x. Positive 1 negative. So the limit is delta x goes to 0. 2x delta x plus delta x squared minus 2 delta x. I know the delta x is annoying, but this is all one variable, and this is all, there's a delta x in each term, so you can factor it out. So if I pull out a delta x, what am I left with on top?
2x plus delta x minus 2.
Right? If you pull the delta x out, you have 2x. Since you have a delta x times delta x, you'll still be left with one of them here, and then minus 2 on the end. All of this over delta x. Cancel, cancel. So then what happens? Now we can plug it in, right? There's no delta x in the denominator. So delta x goes to 0 means I'm going to plug in 0. One more line here. This is just recopying what I have left. But because there's no indeterminate form, it's not 0 over 0, there's nothing undefined, I can just plug 0 in here for delta x, and I'll get 2x minus 2.
Did they describe that anywhere in the book? I couldn't figure
No idea.
the concept of having one variable for.
So you're saying you have two, actually this has two variables, right?
You're using it as one.
Well, yeah, delta x is one variable, but it's separate from x, right? They have nothing.
So is there somewhere in the book that explains that? Because I was trying to find something.
Delta x is a variable?
It's kind of a new concept that I haven't really.
No, I understand what you're saying. I'm not saying you're wrong. There should probably be somewhere where they do it. But I think the assumption is probably that you use this in pre-calculus instead of the h. So you would be used to seeing this. But you didn't, because you came from here, and in here in this college you used a book that used h. So that's why you have a teacher, I guess. What's up?
They do it in 2.
They do it in chapter 2?
Yeah,
Yeah.
I put the heading in 2.
Yeah, so this is the definition of derivative right here. So that's a chapter 2 concept. So they're trying to get you prepared for chapter 2. So when you get there, you don't stumble on things like this, because there's more intense things to worry about. So they probably explain it a little bit in chapter 2. But that doesn't do you any good in section 1.3, I understand. What else? What else gave you trouble? 1.3, 1.4, continuity. Limits.
Zero, like 1.4.
Yeah.
How about number 23? I remember we talked about the greatest integer, but the example that you gave us was just an f of x.
Right.
I'm not really sure how to solve it.
23. Oh, because it's got a couple extra numbers in there. All right.
So of course I just tried to plug it in there and that
Did
didn't
you
work.
quite do it for you, huh? All right, let's look at that number 23. So let's see, it says, in exercise 7 through 26, find the limit if it exists. If it does not, explain why. And then it asks for the limit as x goes to 4, but then it put a little negative up here, right? So that means from the left, of the function 5, greatest integer, x, minus 7. This is the limit we're trying to evaluate. Limit as x goes to 4 from the left of not quite just the greatest integer function, but the greatest integer function times 5 minus 7. The easiest way to do this, in my opinion, is to push the limit in. Remember, we have all these limit rules that say, you know, you can put the limit past a constant multiplication and you can distribute it and all that. So what I would do is get the limit as close to the function as I possibly can. Right? So first you distribute. This will become the limit as x goes to 4 from the left of 5 greatest integer x minus the limit as x goes to 4 from the left of 7. So I just put the limit into each term. Now, some of these are silly. For example, it would be smarter to do the limit as x goes to 4 from the negative right inside of the multiplication, push it past that constant multiple. And so I would rewrite this limit with a 5 out front. And then this limit I can actually evaluate. What's the limit of 7 as x goes to anything? 7, right? That one you guys actually did okay on. So the limit of a constant as x goes to anything is just that same constant. And so what the question comes down to is first finding the limit of the greatest integer function, then multiplying by 5, then subtracting 7. So you kind of have to remember the way the greatest integer function works. Either you need to use a graph or you need to plug in values that are just to the left of 4. So let me give you a graph real quick so you can get used to seeing this. Remember the way 1, 2, 3, 4. So the way the greatest integer function works is when you put in an x value, it gives you the greatest integer that's less than or equal to that x value. So it's always pushing things lower. It's always pushing things down. So if I plug in something between 0 and 1, like 0.5, it's going to give me what? 0. Now what about at 0? If I plug in 0, what do I get? The greatest integer that's less than or equal to 0 is 0 still. What about the greatest integer that's less than or equal to 1? 1. So at the integers, you get exactly what you plug in. But then as you get bigger, like 1.1, 1.2, 1.3, it pushes back down to 1. So this is all at 1. But then once you get to 2, it jumps up to 2. But then 2.1, 2.2, 2.3, it pushes it all down to 2. Once you get to 3, you jump up to 3. But then 3.1, 3.2 pushes it down to 3. Once you get to 4, you jump up to 4, etc. So if I want just this portion, the limit as x goes to 4 from the negative side, from the left, I would be focusing on values on this side of 4, which would bring me up here. I don't even care about this side because it's from the left. So what value am I approaching? 3. That makes sense? You totally ignore this. All the y values right here are 3. 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. So as you get closer and closer to 4, your y values are all 3, 3, 3, 3, 3. At 4, it jumps up, but a limit doesn't care what happens at 4. Right? A limit cares what the trend is around 4. And specifically the trend to the left of 4 because of this negative. So this limit will equal 3. So then you do 5 times 3 minus 7, which equals 3. Instead of using the graph, how else could you have evaluated this? And if you're not sure, or if you're too lazy to really draw a graph, which would be my reason, you could do a table. It wouldn't be that hard for greatest integer. You would do x in greatest integer of x, the function of x. And you plug in things just to the left of 4, right? The negative means to the left. So you do like 3.9, 3.99, 3.999. And you get the limit as you approach 4 from the left. Right? But the way the greatest integer function works, if you take 3.9, it's going to push you down to 3. If you take 3.99, it's going to push you down to 3. 3. So it's clear that the limit from the left of 4 is going to 3. So either this analysis or this analysis or something. Okay, all right. Stop talking. Make sense? Questions? So this first part might have been tricky, but you can always distribute a limit as long as it makes sense, right? As long as you don't get 0 in the denominator or something funny. Other problems? Let's give you a hard time. There's no way that nothing else gave you a hard time. No possible way. I mean, I'll move on, don't get me wrong, but this stuff's not easy.
28, 1.4.
So 28,
The problem that I was having
yeah,
was that I canceled out x plus 1.
uh-huh,
So there's a hole at x plus 1.
uh-huh.
But on the graph, the hole is
Oh, I see.
not there.
So 28 gives you this function, f of x equals x squared minus 1 over x plus 1. And because they're nicer than me, they gave you a graph of this function. Right, they gave you -1, -2, -1, and it's a line with a hole in it. A hole here, 1. So they gave you this graph. And they say discuss the continuity of each function. So basically, find the continuity. Yeah, so if you factor this out, x minus 1, x plus 1 over x plus 1, the x plus 1's cancel, leaving you with x minus 1, but where does this put your hole? At negative 1, because you can't have the denominator equal 0. So your hole is going to come up when x plus 1 equals 0. So the continuity this function is continuous, first of all, you guys understand it's not continuous at -1, right? Why not? Because there's a hole, okay. You have to have three things for a function to be continuous. F of c has to exist, the limit as you go to c has to exist, and they have to be equal. So what doesn't work here? F of c doesn't even exist, right? You remember those three conditions? F of -1 doesn't even exist, so there's no chance of being continuous. But everywhere else you're fine, right? There's no jumps, there's none of our other discontinuities, so everywhere else you're fine. So this will be continuous on -∞ to -1, -1 to infinity. Okay, dokie. Okay, dokie. Artichoke. What else can I do for you? Anything?
Can we do 75, 1.4?
Yeah. Yeah. So number 75 gives you the piecewise function g of x equals, and then it has x squared minus 3x if x is greater than 4. And then it has 2x minus 5 if x is less than or equal to 4. It says to graph this using a graphing utility, but it's kind of weenie. You don't really need a graphing utility to graph this. Unless you count your brain as a graphing utility. So we can graph this without a calculator pretty quickly. But the overall point here is it wants you to use the graph to determine the x values at which the function is not continuous. So my argument or my assertion is that you actually don't need a graph to tell me whether this is continuous or not. I mean, we'll get one and we'll see how it goes, but even before that, in order for something to be continuous, in order for a function to be continuous, basically it can't have any of our jump discontinuities or any holes or any vertical asymptotes or anything funny like that. So let me ask you, if x is greater than 4, is there any problem?
No.
As far as continuity goes? No, it's a problem, right? So these usual polynomial functions are going to be continuous everywhere. So for x greater than 4, there's no problem. What about for x less than 4? What is this? Line. Is a line not continuous? Line's super continuous. It's as continuous as you get, pretty much. So the only place there might be a problem is where they meet up, right? Line, continuous, no jumps, no breaks, no holes. Right? Parabola, continuous, no jumps, no breaks, no vertical asymptotes, nothing fun. So the only problem you might have is at 4. So what you can do, yeah, well, essentially, but yeah. What you need to check is that the limit as x goes to 4 of f of x is equal to f of 4. And more specifically, a little bit easier way with piecewise functions to talk about the limit as x goes to 4 is to do the limit from each side. Right, you can find what happens as x goes to 4 from the positive, and you can find what happens as x goes to 4 from the negative. So how would I figure out what the limit is from the left side of 4? Where do I plug in?
Second one.
The bottom one. Right, the limit as x goes to 4 from the negative means you plug in when x is less than 4,
Get a 3.
and you get 3. This limit is 3. from the positive, you plug in when x is greater than 4. Plug in 4 here, you'll get 4 squared minus,
Get a phone.
yeah, you get 4 squared minus 3 times 4, 16 minus 12. So what this is saying is you're approaching 4 from the right, you're approaching 3 from the left. So this limit doesn't even exist because they're not approaching the same thing. The limits don't even exist. So doesn't even matter if f of 4 exists or what it is. Right? Because this limit doesn't exist. Right? When your left limit and your right limit are not equal, then the overall limit doesn't exist. And if your limit doesn't exist, your function can't be. So your answer as far as the continuity goes, this is continuous for any x value in the interval negative infinity to 4, but not at 4. It's not continuous at 4. As far as the graph goes, if you were going to graph this, how would you graph this parabola?
Down 3.
So it's not going down 3 because of this x. If it were just minus 3 like this, then it would be going down 3. But that extra x, how do you graph that? What does that do?
Moves horizontally.
This affects x-intercepts. If you have an extra x in there, you want to factor and try to find your new x-intercepts. So what's going to happen here, 1, 2, 3, 4, we have sort of our breaking line. For this guy, I would pull an x out. Right? For y equals x squared minus 3x, factor an x out of that. And you get your zeros are 0 and 3. Is the parabola pointing up or down? Up, because it's a positive x squared. Now this is supposed to be for x greater than 4, so this part actually isn't part of my graph, but eventually it pops into existence. And so this is the full parabola, but I only want the part that's greater than 4. And what's this hole going to be right here? Where's this at? And how do you know? Well, you get, it's this guy right here. The limit is x goes to 4 from the right. So this will be a 4 form. Or another way of saying that is if you plug 4 in here, what do you get? You get out 4. So that's what the hole is. On the other side, you have the line 2x minus 5, which means you go down 5. 1, 2, 3, 4, 5. And you draw a line with slope 2. So up 2 over 1. Let's see where this guy lands. And we know if we plug in 4 here, we get 3. So this guy lands at 4. There's a sort of pictorial reason why this function is not continuous. So this notation here, limit as x goes to 4 from the positive, this is the technical notation you use to say plug in 4 in this one. Right? Because you can't write f of 4. Right? F of 4 means you would plug in 4 in this one. But using the one-sided limit, x goes to 4 from the positive, that's the same thing as saying plug in 4 to the top one. And x goes to 4 from the negative is the same thing as saying plug in 4 to the bottom one, because that's where x is located. Did you guys do okay with with your limits in 1.3, the trig limits and the rationalizing and all that? Any problems with that? I mean, we did 61, but any other limits from there I can help you with?
For the trig limit,
Yeah.
question, the last limit on the first page of the review.
Yeah.
Do that one.
This top review sheet here,
Yeah, the monster.
number 21 or number 20?
It
We
wouldn't
can't do
matter.
20 yet because we don't know about infinity.
Oh, yeah, then 21.
We can do 21. Yeah. You're not gonna like it. But we can do it. That's the u for the limit as y goes to 1 of secant of y times secant squared y minus tan squared y minus 1. Crazy, huh?
I didn't get to that one. So I was
Did you,
like, what?
Distribute the secant first.
Okay, so now this is not multiplication, right? So secant doesn't work like multiplication. You can't distribute it.
That's in.
Oh, okay.
It's a function of the.
Secant of that one times.
But what you can do is push the limit through it. Okay? The limit can go inside of the secant because secant is continuous, so putting the limit inside or outside is the same thing. So the way you're supposed to approach this is to just plug in the limit. Because there's no problems. But I don't ever get undefined if I plug in 1 everywhere. Right? Like, for example, where would tangent have a problem?
Pi over 2.
Yeah, tangent has asymptotes at pi over 2, negative pi over 2. Or let's put it like this, undefined at y equals pi over 2, or negative pi over 2, or 3 pi over 2, etc. But 1 is not equal to negative pi over 2 or pi over 2, so you can just plug it in. Same thing here, where's secant undefined? Secant is 1 over cosine. Secant of y is equal to 1 over cos y. So where's cosine 0? Pi over 2, 3 pi over 2, negative pi over 2. So this is undefined in the same place. But 1 is not pi over 2 or 3 pi over 2 or negative pi over 2, so it's perfectly okay to plug it in. Which means you're going to get this limit equal to secant of 1 times secant squared of 1 minus tangent squared of 1 minus 1. Which is not done, but that's the calculus. Right? Because nothing's undefined, because we don't get 0 over 0, nothing indeterminate, we can just plug it.
And then, oh, you use your calculator.
No, calculator. Oh. What's secant squared minus tangent squared?
1.
So this is secant squared of something. The 1 times doesn't change anything, right? So secant squared of an angle minus tangent squared of the same angle minus 1. And you should have an identity. Remember back in trig, you had things like cos squared theta plus sine squared theta equals 1. And if you divide everything by cosine, for example, you get 1 plus tan squared theta equals secant squared theta. So this identity, if you move the tangent over to the other side, tells you that this simplifies to 1. So then you have secant of 1 minus 1. 1 minus 1 is 0. Secant 0, you plug 0 in the cosine.